You ever wonder how your computer does it all? You're streaming music, a game is running, files are downloading, and somehow it all just works flawlessly. Well, it turns out it's actually a really clever illusion. And today, we're going to pull back the curtain on the CPU's incredible high-speed juggling act.
I mean, really think about it for a second. Right now, you're watching this, maybe your email is syncing in the background, you've got a dozen browser tabs open. It feels totally simultaneous, right? But how in the world can one single processor be in all those places at once?
Well, here's the secret. It can't. Multitasking is a brilliant, brilliant trick. Your CPU is actually a master of doing one thing at a time, but it switches between tasks so fast, we're talking nanoseconds fast, that to our slow human brains, it feels like everything is happening at once. And this whole high-speed performance is directed by a set of rules called CPU scheduling.
Okay, so how does the CPU decide what to do next? There are a few different playbooks or algorithms it can use, and the first one we're going to look at is all about playing favorites. It's about creating a VIP line for your computer's most important jobs. It's called priority scheduling.
It's a pretty simple idea, but it's incredibly powerful. Every single task, or what we call a process, gets a priority number. So when the CPU is free, it doesn't just grab the next thing in line. Nope. It scans the whole queue, finds the process with the absolute highest priority, and runs that one first. It doesn't matter when it showed up.
And this is the perfect real-world example. You know how it works in an ER? A patient with a life-threatening injury who just came in is going to be seen way before someone who's been waiting for an hour with a sprained ankle. It's all about handling the most critical needs first. Your computer does the exact same thing, making sure that moving your mouse gets priority over, say, a background update.
So let's see how this plays out. Here we've got 3 processes, and notice the priority numbers. In most systems, a lower number means a higher priority. So process P2, with the priority of 1, gets the CPU's attention first. After it's done, P3 is next up. And finally, poor P1 with the lowest priority gets its turn. The order they arrived in? Totally irrelevant.
But like any system that plays favorites, this approach has a dark side, a potential flaw. What happens if the VIPs just never stop coming? This leads us to a classic problem in computing called the starvation problem.
And this is a really important question. If your system is constantly dealing with high-priority stuff, keyboard clicks, system alerts, all that, what happens to that low-priority process that's just been sitting there waiting patiently? Could it just wait forever? And the scary answer is, yeah, it could. That's starvation, where a process is just endlessly ignored, never getting a chance to run. So to fix this, operating systems have this really elegant solution called aging. Basically, the longer a process waits in line, the higher its priority becomes. It's like it gets a little bump in importance for its patience. Eventually, even the lowest priority task will age enough to finally get its moment in the spotlight.
All right, so priority scheduling is all about that VIP treatment. But what if you don't want VIPs? What if you want a system that's built on pure, simple fairness? Well, that's where a totally different strategy comes in. It's called round-robin scheduling.
Round-robin is the great equalizer. It gives every single process an identical slice of CPU time. This little slice is called a time quantum. A process runs for its quantum, and then, whether it's finished or not, it gets paused and sent right to the back of the line. This way, everybody gets a turn.
The perfect way to think about this is a well-run classroom discussion. The teacher says, okay, everyone gets exactly 30 seconds to speak. When your time is up, you stop, and it's the next person's turn. It stops one person from hogging the whole conversation, right? Round Robin does that exact same thing, but for your computer's programs.
So here's how that cycle looks. Let's say our time quantum is 2 milliseconds. P1 runs for its 2 milliseconds. Then it's paused. The CPU instantly jumps to P2 for its 2 milliseconds. Then P3 gets its 2 milliseconds. And after P3 is done, where does it go? Right back to the top to give P1 another turn. It's this constant, fast rotation that makes your computer feel so responsive.
Now, this fair and square system sounds perfect, doesn't it? But there's a catch. There's a hidden complexity. The entire performance of a round-robin system depends on getting one little number just right. It's a real Goldilocks dilemma.
That magic number is, of course, the length of the time quantum. See, if it's too small, the CPU spends all its energy just switching between tasks, without actually getting much work done. It's all overhead. But if the time quantum is too large, then a big process can hog the CPU for ages, and everyone else has to wait, which makes the whole system feel slow. It kind of defeats the whole purpose. It has to be just right.
So what we're seeing here is that there's really no single best way to do this. There's no one-size-fits-all scheduling algorithm. Priority scheduling is fantastic for making sure urgent things happen now, and round robin is amazing for making everything feel fast and responsive. It's all about having the right tool for the right job.
And in the real world, your operating system's toolkit is even bigger than what we've talked about. Modern systems are incredibly smart. They often use hybrid schedulers. So for example, it might use round robin for most of your apps to keep things snappy, but instantly switch to priority scheduling the moment a critical system process pipes up. It's this intelligent mix and match approach that makes everything feel so seamless.
So the next time you click something and it feels instant, just remember it isn't magic. It's the result of billions of incredibly fast, super smart decisions being made every single second. It's that invisible traffic cop inside your CPU constantly deciding which task gets the green light. The only question is, which one of these clever strategies is it using right now?